Hello everyone, welcome back to the second tutorial. In this tutorial, we will extend the linear Gaussian model and introduce the generalized linear model. In the first tutorial, we showed how to use the linear Gaussian model to predict spike counts from stimuli. But after doing the exercise, I believe people have already seen that the predicted spike counts are not matching the true spike counts very well. The main reason is that the observation noise is not Gaussian. The neural response is spike, which is non-negative and discrete. Gaussian works for continuous variable in the interior domain. Therefore, we need some other noise distribution and nonlinear function to do the spike train encoding. That's why we need to extend the linear model to generalized linear model. A typical diagram for a linear model is as this form. X is the input, pass it through a linear function, and input to a noise distribution function to generate y. The noise distribution here is usually considered to be distributions from exponential family, which I'm not going to expand too much here. An example would be linear Gaussian model. Y is equal to theta multiplying x plus eta, which we've already mentioned many times. Well, a generalized linear model has this following diagram. X is the input, pass it through a linear function, then pass it through another nonlinear function, finally input to a noise distribution function to generate y. A main difference is the additional nonlinear function in the middle. An example GLM could be nonlinear Gaussian model. There is a nonlinear function f mapping x theta multiplying x to y. The inverse of this f function is called link function that provides the relationship between the linear predictor and the mean of the Gaussian distribution. Another popular example of GLM is Poisson GLM. There is still a nonlinear link function there, but the noise distribution becomes a Poisson distribution. This Poisson GLM is generally very powerful for spike train encoding. Therefore, we're going to focus on Poisson GLM in the rest of the video. Before diving into Poisson GLM, I want to briefly introduce Poisson distribution. Poisson distribution is usually used to model the number of events. In our case, they are spikes, occurring within a given time interval. In the example we gave, we have one spike or no spike at all time points. We could bin the spike train with a certain time interval and count the number of spikes within the time bin. As a result, we reformulate the spike train data with binary spike count into a new sequence. The x-axis is the index of time bin, and the y-axis is the spike count within each time bin. Now we have a new sequence of the spike counts, which are discrete values. We could generate a histogram of spike count y from this new sequence. The x-axis now is the spike count y, and the y-axis is the probability of y taking each discrete value. We can see in this example, most of the spike counts are small, like below 5. Given such a histogram, we could use Poisson distribution to describe such a probability mass. The probability mass function is given by this form. Small y is the observed discrete spike count. Lambda is an unknown parameter defining the function. It has to be larger than 0. And notice that the denominator y factorial doesn't include lambda here. We can plot the mass function given different lambda values drawn on the right here. The smaller lambda, the more concentrated to the y-axis. And we can see that lambda is equal to 1 might lead to a better mass function matching the histogram of the observed spike count we have here. In Poisson GLM, lambda has a physical meaning, which is the firing rate, written as lambda is equal to f of theta transpose multiplying x. After introducing Poisson distribution, we could talk about how to define Poisson GLM now. Poisson GLM has this diagram. The inverse of link function f for Poisson GLM is usually chosen to be exponential to guarantee the non-negativity of the firing rate lambda. We know the probability mass function for Poisson distribution, P y is equal to small y, and the probability function is equal to lambda y e to the minus lambda over y factorial. Writing it in the context of temporal filtering model, we can now assume the encoding distribution to be p yt given theta xt. It is equal to the above mass function when capital Y is equal to small t and lambda is the firing rate lambda t. We further write it out by replacing lambda with f of theta multiplying xt. To optimize for the linear filter theta, we could write down now the log likelihood. Similar to the linear Gaussian model, the log likelihood function is the log of the probability mass function, which is a product of pyt given theta xt over all time points. We then bring the expression of the mass function into the logarithm. Next, we move the product to the outside of the logarithm and separate the log into two terms. The first term ends up to be a summation of yt multiplying log f minus log of yt factorial. And in the second term, the logarithm is cancelled by exponential, thus leaving us a summation of f. We notice that the second term here in this last line doesn't involve theta, thus it's a constant term during the optimization. We could further clean it up into this form. And finally, we can rewrite it in the vector form, throwing away the sum. To find the maximum, we need to solve an equation which is the derivative of log likelihood with respect to theta is equal to 0. But this equation has no closed form solution. However, the negative log likelihood is a convex function, and so standard convex optimization techniques such as gradient descent can be applied to find the optimal value of theta. Usually, in neural applications, a linear temporal filter would look like this. And filling it into the Poisson GLM diagram, we can now generate spike counts given input stimulus. The shape of this linear filter indicates that the neuron is the most responsive to the stimulus with such a temporal pattern. In the following notebook, you will continue the fitting for the same stimulus and spike count data, but you fit Poisson GLM by optimization and predict spike counts. You compare the prediction from linear Gaussian model and Poisson GLM. Hope you enjoy that.